All right, everyone, we are back and we are going to do our Pset 7 solution videos. So first we're going to look at, is the system an LTI system and causal or not? And we're going to basically go ahead and answer some of those questions. So let's go ahead and look at our first system. Is this function linear? Yes. Is it time invariant? Yeah, I don't see any kind of input. And is there any other inputs or outputs basically that depend on some time that's less than our input time here? Nope. So we're good. We're LTI and we are indeed causal. Next system, linear. Looks good. Are we time invariant? Uh-oh. Nope. Because it's dependent right here. So are we causal? Yep. This order is basically right here. We're higher order for our output over the input. So we are causal. Let's look at the next system here. Are we linear? Are we linear here? Nope, unfortunately not because of this function. So we are not linear. Are we time invariant? Yep. Are we causal? Yes, we are. All right, let's look at the next function. This one's a little tricky. Are we linear? Yes. Are we time invariant? We're actually not here because, again, anything for time greater than basically time equals to 1, it needs this future input that's ahead. So basically our input is ahead, we need kind of this future relative to our t here. So unfortunately that's not the case. And we are also not causal as well. And then finally, this last function here, are we linear? Nope, because we have this kind of +5, this kind of, additive constant. So we're not linear. Are we time invariant? Yep. Are we causal? Indeed, we are. So that's our kind of system here. So let's actually, all right, everyone. And I needed to, sorry for the abrupt switch. Let's go ahead. I'm going to open up my Mathematica and let's go to this next problem. So let's look at the following transfer functions, and we're asked, for all systems that are LTI, so that are indeed causal. And so actually, let's look at this. So this looks okay. Again, we need the denominator to be of higher order than the numerator. So we're not even going to touch this one. So already, I'm not going to do work for this function. So we need to solve for the poles and the zeros. We need to plot the poles and the zeros in the estimate name. And based on it, let's kind of qualitatively talk about what the system's going to look like. So we have our transfer functions here. We have our handy-dandy pole zero plot simple function. So for PS1, we can see, as we might expect, we have a single pole at -2, and we can see that on our graph. So how is that going to look like? What's the response to that function? If we only have a real pole, so that means we're going to get some exponential decay. So kind of like extremely damp, so very exponential decaying response. If we look at PS2, now we actually have 2 poles that have both a real and an imaginary component. So we're just basically going to have an envelope that's going to exponentially decay because we are basically in that left-hand plane. And we're going to have some oscillations that are going to be governed by the magnitude of that imaginary component. So that's what the system's going to look like. What about PS3? PS3, let's look what we got here. So we have a 0 here, and we can kind of see that at -1. And we also have two poles that have, again, a real and imaginary component. If this was closer, we might kill some other components that appear in some of the responses of our exponential decay, but we're pretty far apart. So again, we're going to expect some exponential decay envelope with some oscillations that are governed by the magnitude of that imaginary component. What about PS4? We actually see we're going to have basically a pole at 0, a 0 at -4. So it's really going to kill this response. So this 0 here may kill this pole response here, and we're going to kind of be dominated by that exponential decay that's governed by that real pole to the left there. So, excellent. I would definitely suggest exactly the time response to confirm that qualitative description, and I'm looking forward to see that in your solutions. Great. Now let's look at the following system. Let's go ahead, and it's what we did in the last problem set. So we can define those values and the values from the previous problem set. And actually, remember, if we're going strictly speaking, the control command, it should be 1 over S here and here. So we're going to have basically no zeros here, and we're going to have this kind of pole, one pole that's located here, no zeros, and then that imaginary component as well. So when we look at the time response of that system, again, we should see that envelope and then of exponential case plus some oscillations, again, due to that damping component. So cool. And should look very similar to our last function. Fantastic. Now, let's look at each of these kind of 3 kind of pairs of graphs, because they're very important. So we remember from our notes, we can kind of describe essentially what's going on here. So in this system, it looks like we have the same relative kind of decay function, but we're seeing the oscillations are like drastically decreasing. So what could be going on here? Well, if we look at our S domain, these clearly have even, there's some kind of imaginary component to this system, right? So let's say we're stuck on, or let's imagine, it could be possible, that all of these have the same envelope and the real response here. This one that has increased oscillations would be the highest here. And then probably this next, so basically if this is 1, 2, 3, we'd be 1, 2, and 3 here. And the corresponding mirrored pole as well. So you're just going to look at us, you can kind of write any imaginary function that's second order, right? Plus S plus, B, and just get a complex, essentially 2 complex poles that would just basically vary in the magnitude of that frequency response. So lots of different values that could kind of come out from this. What's going on here? Actually, let's save this one for last. I really like this response. Let's look at this one. So here, really, there's almost no oscillation. So I would say if this is 1, 2, and 3, and if I'm looking at my S domain, imaginary, looks like we have real poles that basically 1 would be here because it's the most negative, and then looking at kind of the response, it's kind of a toss-up. I'm trying to look at how the magnitude is changing. So let's look at maybe 2. So maybe this is a kind of quicker drop here. So then maybe this would be 3 and maybe this would be 2. But again, this is definitely a real response. There's really not any oscillations and we've got it. Now, what about this one here? This function, we're somewhere over here. So we have, whatever this is, let's call this A, B, C. This is over here. So it's exponential, it's real, it's in the there's something that's in the right-hand plane, and that we're going to see in a bit. This is an unstable system. Here we're getting, oscillations. So we might be lying, and this could be looking like a marginally stable system. We'll go back to that in a little bit. But we could be lying essentially here and here. And actually maybe B is here, like right on this point, and maybe C is here because, again, the frequency of that oscillation is decreasing between the two. So any transfer function that will kind of reach that, we're good to go. So thanks, and I'll see you in the next video. Bye.